Hello everybody and welcome to Intergalactic Construction. This is the first lecture for Dynamics, Engineering Dynamics Mechanics. I'm going to do a quick overview of the course here. We got kinetics and kinematics of both particles and rigid bodies. We'll explain the difference between those two. Mass and acceleration, work and energy, impulse and momentum, introduction to the kinetics of different mechanisms, such as a piston in a cylinder is a good example. We're also going to talk about 3D rigid body dynamics at the end of the course. A couple things you should know coming into this course. You should probably have a good basis in statics, calculus, and physics. I believe that you can take this course simultaneously with physics, but it is good to know all these three courses. I know that statics is typically a prerequisite for this course, as is Calculus 1 and Calculus 2. Alright, this is the style of lectures that I'm going to be giving. They're going to be very brief, very fast-paced lectures. They're going to focus more on the problems, actual problems. We're going to be walking through real dynamics problems and not too much of the theory. I'm going to try and fly through the theory because normally if you're going to class, you're going to be seeing the theory there. If you don't understand it, you don't understand it. That's it. You want to know how to do the problems. So these videos are going to teach you how to do the problems and show you step by step and explain each step on how to solve dynamic problems. All right, let's begin. As I said, the first topic is the kinetics versus the kinematics. Kinetics is the study of the relations existing between the forces acting on a body, the mass of the body, the motion of the body. Kinetics is used to predict the motion caused by given forces or used to determine the forces required to produce a given motion, where kinematics also involves the geometry of the motion. You have displacement, velocity, and acceleration, and time without reference to the cause of motion. That's the main difference, without reference to the cause of motion. Now let's start talking about the types of motion that you will see. You will see either rectilinear motion or curvilinear motion. Rectilinear, moving along a straight line. Curvilinear, moving along a curved line. Could be 2 dimensions, could be 3 dimensions. Okay, now it's time to drop into gear and solve some problems. So let's drop in, just like this guy dropped in.
There's going to be some noise going around me. This is just part of the whole experience, but as you can see, this is what they call the gantry lift. Now the doors are closing.
Alright everybody, welcome back. Let's jump right into a couple of formulas that we're going to need to use to talk about the language of dynamics so we can start solving some problems. Now we have x equals position, v equals velocity, and a equals acceleration. Okay, now how do we convert between these two? Well, velocity is the derivative of position with respect to time. Acceleration is the derivative of velocity with respect to time. So, if acceleration is the derivative of velocity with respect to time, that means it is also the double derivative of position with respect to time. We also need to make sure that we're not confusing vectors and scalars when we're talking about dynamics. A scalar is a quantity. It is a magnitude. If your car is traveling 60 miles per hour, is that a scalar or is that a vector? That is a scalar. It is just the magnitude. If you say it's going 60 miles per hour and it's traveling directly north. Now you have a vector. A vector shows not only magnitude, but it also shows direction. Okay. So now that we have all of that done, if you have any trouble with vectors, scalars, all that stuff, make sure you go back and review. I'm sure there's some videos that will help you out with that. But you do need to have a good understanding of the two to continue forward. Now let's talk about the main formulas that we're going to be using. The main formulas. Let's say that we have constant, and I'm just going to give you the formulas. I'm not going to derive them. Just give them to you. These are the main formulas you're going to use throughout dynamics, so make sure you learn them. I'm sure they'll be given to you on tests and stuff like that. If not, just memorize them. It's not too complicated. So let's say we have a constant velocity. Then the change in position equals initial position plus initial velocity times time. Okay. Well, what if we don't have constant velocity, but we do have constant acceleration? Okay, well, what do we got there? We're going to have three formulas here that are very common. The change in position now equals initial position plus initial velocity times time plus 1/2 acceleration times time squared. All right. What about our velocity? Our velocity will equal initial velocity plus acceleration times time. Very similar to this one over here. Now, this is called the timeless equation. There is no variable time in here. So if you see a problem when you're doing dynamics and there's no time isn't given, normally you're going to go to this formula. Velocity squared equals initial velocity squared plus 2 times acceleration times delta x, or change in position. Alright, so these are the kinematic equations. You've probably seen them in physics. You're going to use them throughout dynamics. It is going to get more complicated than just these equations, but this is kind of the launching point. So make sure you have a good understanding of these equations and be ready for the first chapter or two of dynamics. You're going to be reaching into this bag constantly. And we're going to jump into some example problems right now. So we'll be using a few of these. Okay, so let's do a quick example problem here. Let's just say Ben Affleck is thrown off a 50-foot tower, and when he is thrown from this tower, he has an initial speed of 18 feet per second. Now, as you immediately notice from this question, what do you not see? You don't see any variable that has to do with time. 18 feet per second is a velocity. Yeah, it's a velocity because we know the direction. The direction's down. All right, so we have, which formula do we want to grab out of the kinematic equations? Probably velocity squared equals initial velocity squared plus 2 times the acceleration times the change in position. So we could also write that as delta x equals x1 minus, x2 minus x1. Now the two things we want to find out, I didn't write it in the question, sorry about that, but you want to determine the speed of Ben Affleck when he hits the ground and how long it takes him to hit the ground. Okay, seems easy enough. We can use this formula to do it. So the velocity squared. What's the initial velocity? Well, Ben Affleck started at 18 feet per second, so that's going to be 18 squared. What is the acceleration? Well, the acceleration of gravity is A equals 32.2 feet per second squared. That's a constant. That's gravity. If it were in metric, be 9.81 meters per second squared. Okay, but we're not in metric. Always pay attention to that too. We are in the American units. America. So 2 times 32.2. This is a parentheses. Our acceleration is 32.2. And what's the change in position? Well, if you look, he starts off here, right? Then he makes a Batman movie, and boom, down he goes. All the way down to the bottom. 50-foot tower. A 50-foot tower. So, $50 minus 0. Easy enough. The change in position is, in fact, 50. So now we can say that the velocity squared equals 18 squared. Oh, I don't have my calculator. $18 squared is 324 plus 2 times 32.2 times 50. So 3220. Okay, so the square root of those two numbers added together is going to be, and I'll try and go through this because you can pause and do it on your own. It's good to do these on your own, by the way. 59.532 feet per second. This is the speed at which Ben Affleck smacks into the ground. Now that we have we're solving for time for the second one. We want to know how long does it take him to hit the ground. Remember, how long does it take Ben Affleck to hit the ground? This is how fast he's traveling when he hits the ground. So we're going to need another formula, another one of the kinematic formulas. Velocity at the second, current velocity equals initial velocity. Let's put it that way. Current velocity equals initial velocity plus acceleration times time. Boom. All right. So we're going to say your current velocity is 59.532 equals 18. That was your initial velocity plus 32.2 times t. All right. Boom, boom, bam. All in all, it took Ben Affleck 1.29 seconds to reach the ground from a 50-foot drop. Okay, well, let's do another one. Okay, and we're back with another problem here on intergalactic instruction. Now we got a train with Ben Affleck on it. It's traveling at a velocity of v equals 3t squared plus 2t. We need to determine Ben Affleck's position at t equals 3 seconds. Also determine it for t equals 0 and x equals 0, position equals 0. Now I picked this problem because although you can go to the kinematic equations, and the kinematic equations are your place to start, sometimes when you have a function in there, it might be easier just to stick with the original equations that I gave to you, which were velocity equals dx dt and acceleration equals dx squared dt, the double derivative of position. Velocity is the derivative of position. Acceleration is the double derivative of position, or just the derivative of velocity. You could also say it is the derivative of velocity. Right? So we know that much. And with this equation, we're given an equation here. Velocity is given as an equation with the variable in it being time. Let's scroll down and get some room here. Let me just copy this formula. 3t squared plus 2t. Right, and then that's all we really need to know. We're solving for it at t equals 3 seconds. So what's the velocity at t equals 3 seconds? Just plug it in, right? What's your velocity at 3 seconds? Well, I should have wrote a 3 in there. 3 squared plus 2 times 3. But that's not what it's asking for. It's asking for our position and our acceleration at 3 seconds. Alright, fair enough. So what was the equation that was given? Velocity equals the derivative of position with respect to time. Okay, how can we rewrite this? What if we pulled that dt over to the velocity side? V dt equals dx, right? Velocity times the infinitesimal increment of time equals an infinitesimal increment of position. Fair enough. When we see this happening, we can pretty much predict what's coming next, right? We're going to take the integral of both sides. We got a dt and a dx. Let's take the integral of both sides, or integrate both sides, I guess you should say. From x to 0, dx. Okay, so I just switched them. And the other one will be with time. V dt. But what does v even equal? V equals this, 3t squared plus 2t. So we can further this equation by saying 3t squared plus 2t dt. And then we can integrate it. Now we have something to work with. We can integrate both sides, actually. We can integrate this side and this side. And we know that the integral of dx is just x. And this is also an easy one to integrate. And hopefully you still remember how to do this. The integral of 3t squared, you add 1 to the top and then divide by that number. So it's going to be t cubed, I believe. Yes, it'll be t cubed. Plus t squared. Simple enough. Position x equals t cubed plus t squared. So now what do? We plug in A3 on those locations. Just plug and chug. 27 plus 9. And I didn't give units in this problem, so we won't worry about units. Your position's just 36 units. Now, let's go to the next part. We have solved the equation for position. This is our position at t equals 3 seconds. We did that through integration, and we manipulated our equations. Now, our acceleration, as I said earlier, is dv dt. So it's actually easier to go this way. I probably should have started that way. dv dt, d dt, and put in the equation for velocity, which was 3t squared plus 2t t. And take the derivative of it. I've always thought taking derivatives is easier than integration. So what do we get? We get 6t plus 2. Our acceleration at 3 seconds, let's write it properly. Our acceleration at 3 seconds equals 6 times 3 plus 2. Bippity boppity. 18 plus 2. What do we get? 20 units per second. Whatever unit that they would have put in the equation, that's what we get. Now, didn't this problem ask for something else? And as you can see, it was easier just to directly manipulate the equations rather than messing with the kinematic equations. Although you'll learn very quickly in this subject, each problem there are so many ways to go about solving it. So you kind of gotta pick which ways you like the best and try to use those, and when those don't work, move on to a different technique. Also, solve it for at t equals 0 or position equals 0. So at t equals 0, it will be 0. Yeah. So our equation for position was this. X equals t3 plus t squared. If we put a 0 in there, x will equal 0. Our initial acceleration, however, will be a little bit different because we have a constant in there. Our equation for acceleration is 6t plus 2. So what's our initial acceleration? Well, you put a 0 in that equation. 6 times 0 plus 2. What do we get? We get 2. 2 units per second. You can say feet, whatever. And those are our answers. Okay. Thank you, and I'll see you in the next lecture. The next lecture will mostly just be problems. I'm probably going to stop lecturing and just solve problems. The more problems you do in this class, the better understanding you're going to do. That's all I would do to study, is just do problem after problem. I mean, read the chapter once, twice. If you understand it, good. But problems are the way to go for dynamics. All right, thank you.